Imagine stepping into an intricate dance, a dance of forces that shape everything we know. It's a dance of atomic structure, molecular structure, and temperature, mysterious, deeply fundamental, and indispensable to our understanding of the universe. If you were to navigate the fascinating world of electricity, this dance, this triad, serves as your guiding compass for it, underpins the core of voltage and resistance, the cornerstone of electrical currents. Their interplay, their synergies, their delicate balance form a complex narrative, but by untangling it, we gain a profound understanding of the principles that govern not only electricity, but also material behavior on a macro and micro level. This triad sets the stage for understanding the nuances of voltage and resistance. They inform us on how the flow of electricity is governed, shaped, and even hindered. The dance of atomic structure, molecular structure, and temperature underlies the critical concepts of electrical conductivity and resistance, powering the world as we know it. Get ready to embolden with a newfound perspective as we delve into this fascinating triad and its profound influence on voltage and resistance as we unwrap the first lesson in this electrifying series on electricity and material science. A. Atomic structure. An atom, the smallest constituent unit of ordinary matter, can be seen as a miniature solar system. At the crux of this system is the nucleus, a dense core comprising of protons carrying a positive charge and neutrons that are electrically neutral. The nucleus is the sun of the atomic world, and it forms the atom's identity. Wrapped around this nucleus are layers or energy levels of electrons that resemble the solar system's planetary orbits. Electrons, bearers of negative charge, inhabit these layers. To visualize, these are like concentric circles, with the innermost circle capable of hosting 2 electrons, the next 2 circles able to house 8 each, and so on. Each layer is further partitioned into sublevels with distinct numbers of orbitals. The electron configuration, or the arrangement of electrons in these layers, directly involves and affects a material's properties. This arrangement determines an atom's bonding characteristics, its magnetic attributes, its level of reactivity, and even its physical state under shifting conditions. An instance to see is that of copper, frequently used in electrical wiring due to its excellent conductivity. At the atomic level, copper, Q, possesses 29 electrons, including a rather free outermost electron, 4s1, that has the liberty to move about within the copper's crystalline form. This free electron can be readily displaced by an applied electric field, enabling an electric current to surge through the copper wiring. These free electrons act like a sea of particles in a metal, accounting for its high electrical conductivity. This deeper understanding of the atomic structure primes us for a grasp of the molecular structure, which together with atomic structure forms the intrinsic material properties. These structures, partnered with factors like temperature and energy states, weave the physical and chemical tale of a material. The story of a material property does not stop at individual atoms. It extends to how these atoms arrange themselves in a repeating pattern, forming what's called a crystal lattice. This spatial arrangement of atoms or molecules, chronicled into a 3-dimensionally repeating pattern, is what we refer to as the molecular or crystal structure of a material. The lattice points in this array could signify a single atom, a group of atoms, or an identical molecule, all depending on the material type. What's interesting is that different properties are exhibited by different materials, not only due to the type of atoms participating, but more importantly, due to how they are ordered in the crystal lattice. Graphite and diamond, both fellow carbon atom assemblies, despite their similar atomic composition, sport vastly differing properties due to their distinct crystal structures. One metal of particular interest in this context is copper, which boasts an efficient crystal structure. This face-centered cubic structure, or FCC, means that every copper atom inside this lattice is neighbored by 12 other copper atoms. This manner of atom packing is highly efficient, creating a uniformly conductive matrix traversable by cushioning free electrons. Bend or twist a wire of copper and it still maintains its electrical conductivity. This is because the FCC lattice, organized and compact, enables the outermost electrons to wander equitable throughout the lattice structure, making conductivity possible. Understanding the molecular structure paves the way for uncovering the role of temperature and energy states in a material's properties. Together, atom structure and the molecular structure and configuration are the building blocks of the material universe, shaping our understanding and application of these materials in myriad ways. The atomic and molecular structures lay the groundwork to understand a material. But there's an eminent external factor that meets these intrinsic material properties and influences them: the temperature. Temperature, in simplistic terms, is a measure of heat energy. This heat energy, provided from external sources, impacts both atomic as well as molecular structures, and hence is significant in modifying the behaviors and functions of materials. At the atomic level, the dynamics get interesting. Temperature boosts the kinetic energy of atoms and molecules, inducing and intensifying their vibrations. As we turn up the heat, the vibrations become more vigorous, a kinetic upheaval disrupting the sea of free electrons. In metals, disturbance in the sea of free electrons, the very essence of electrical current, increases electrical resistance and reduces conductivity. At the level of crystal structure, temperature plays its part by influencing phase changes, transitions of a substance from one state of matter to another. A solid can melt into a liquid, and a liquid can vaporize into a gas as heat multiplies. During phase change, as the crystal lattice unravels, this transforms material properties. From strength to hardness to transparency to conductivity, all are changed. The story of copper as an excellent electrical conductor can't be completed without considering the role of temperature. While its atomic and molecular structures attribute to its excellent conductivity, the application of sufficient heat energy can overpower its internal bonds. Temperature emerges as a pivotal player, influencing atomic movements, molecular alignments, and energy states, steering material properties in new directions. Heat from environment or current can cause the metal to melt, severing a connection. This temperature-induced transformation, not unique to copper, underlies the principle of a fuse. Within these phase transitions, within the intricate tapestry of atomic and molecular structures, electron movements and energy states become mere variables for the engineer or hobbyist. We witness a manifestation of the Dharma, reflecting the interconnectedness and harmonious influence of three elements that contribute to and are shaped by each other. No single negation or relationship between two variables can ever explain a triad fully. Only by identifying and understanding the three factors involved do we comprehend. In the triad, bind an atomic and molecular structure with kinetic energy, we also draw analogy to bhakti, devotional love, in the logic of inclusion. Here, the atomic structure defines the possible molecular structures which, along with the atomic structure, respond to temperature by establishing conductivity, among other attributes. This relationship reflects devotion and surrender, where all individuals contribute to and are affected by their greater purpose. Devotional love for a greater cause guides the individual in aligning their actions conducive to a goal. Atoms and molecules are guided by the heat of the material to transformations in structure. As in all things, three components must be considered together to understand. Thus defines a basic triad of the universe's fundamental logic, and bringing us all one step closer to God. Amen.